The unique representation theorem is just a clever little theorem that says for every x in a vector space, if B is a basis of that vector space, then x can be written in only one way according to that basis. Okay, so if we think about it, let's just look at the proof here. First of all, we're going to assume that x is a member, x is just a vector in V. Then since B is a basis for V, x can be written as a linear combination of the elements of B. So in other words, think of this as just a vector equation where our C's are scalars, and I guess I should notify that those B's are actually vectors, and then of course x is a vector as well. Maybe that helps you to see it a little better. Okay, and the idea is to show that this is unique. So one of the ways that we prove uniqueness, or the primary way that we prove uniqueness, is to assume this is not unique, and if that's the case, then there exists D's, a set of scalars D's. I'll just say then there exists D1, D2, up to Dn, so that we can write x according to the D's. So in other words, there's two ways to write it. Okay, so what we have is automatically we can write it one way because it is a basis, and then if it's not unique, we can write that same x in two different ways. Well, what we can do is we can subtract those two lines, and we get that x minus x is equal to the 0 vector. And then we're just going to say, all right, so 0 is equal to C1 minus D1 times B1 plus C2 minus D2 times B2 plus Cn minus Dn times Bn. Okay, so basically I just took this line again, and since this is also equal to x, I subtracted them to get this line. Well, what this brings up is that now I have a linear combination of the vectors b sub n that is equal to 0. And since our b sub i's are linearly independent, and that's just by definition of a vector, a definition of a basis, and I have it set equal to 0, our definition of linearly independent says that each of our coefficients then must equal 0, and that goes back to our definition of linear independence. So we have C sub I minus D sub I is equal to 0 for each of our i's from 1 to n. And if C sub I minus D sub I is equal to 0, then that's going to give that C sub I is equal to D sub I, and thus we have a unique representation. And so again, what the unique representation theorem says is that we have, for every basis, each x in the vector space can be written as one and only one way according to that basis.